This is linear algebra, section 2 of chapter 1, section 1.2, on vector addition and scalar multiplication. And here we are going to learn how to do algebra with vectors. So if we have a vector, x1, x2 to xn, Rn or Cn, it doesn't matter whether these are real or complex coordinates. And maybe I will write F to denote either R or C. So if I write F, I mean it's the real or the complex numbers. It's true for R, and whatever statement is written is true for R, and if it's true for C, so we just write this as in Fn. And if I let Y be another vector of the same dimension in Fn, we define vector addition . So I want to add two vectors in n dimensions and get another n-dimensional vector. And then all you do is just add coordinate-wise. So this is x1 plus y1, x2 plus y2, down to xn plus yn. So for example, if x is the vector 1, 2, 3, and y is the vector 7, 8, 9, x plus y, 1, 2, 3, plus 7, 8, 9. When you add, 1 plus 7 is 8, 2 plus 8 is 10, 3 plus 9 is 12. Let's just say I'm working on not true. Everything is true equally for complex. This is how you add vectors. And I also want to be able to multiply a vector by a number. And in linear algebra, a scalar just means number. So scalar is number. And I'm going to define scalar multiplication. So in scalar multiplication, we take a number or a scalar C, and we want to multiply it, a vector, by C. So this is C times the vector x1, x2, down to xn. And you simply multiply each coordinate by the scalar C. So for example, 5 times the vector x, that's 5 times the vector 1, 2, 3. 5 times 1 is 5, 5 times 2 is 10, 5 times 3 is 15. So this is the definition of scalar multiplication. And addition and multiplication of vectors satisfy the familiar properties that addition and multiplication of numbers satisfy. So these are certain properties of vector addition. First, it is commutative. So for any vectors x and y, x plus y equals y plus x. It is associative. You take three vectors, x, y, and z. You take x plus y and add it to z. That's the same as adding x to y plus z. Third, there is a zero vector, which is the vector where all the coordinates are 0. And the zero vector has the property that 0 plus x and x plus 0 are always equal to 0. And finally, if x is the vector x1 up to xn, then define minus x, or minus 1 times the vector x. That's minus 1 times the vector x1 down to xn. When you multiply the coordinates by minus 1, you just get minus x1 minus x2 down to minus xn. And if you add x plus the vector minus x, that's x1, x2 down to xn, plus minus x1 minus x2 down to minus xn. So when you add coordinates, this is x1 minus x1, x2 minus x2, xn minus xn. That's 0. So that's the 0 vector. So for any vector x, here's a vector which is in fact this vector minus x, and x plus minus x is 0. And if you like, we can define vector subtraction. The vector x minus the vector y means x plus the vector minus y. So if x is x1, x2 to xn, and y is y1, y2 down to yn, then x minus y is x1, x2 to xn, plus minus y1 down to minus yn. So you get the vector x1 minus y1, x2 minus y2. We just subtract coordinates step by step. That's exactly what you would do. So this tells us how to add and subtract vectors. And what nice properties they satisfy. Similarly, scalar multiplication satisfies some very nice properties. If you multiply the vector x, so if x is in Rn, and c is a scalar, a number in R, so you take the number 1 and multiply it by x, you just get x. If you take two different numbers, c and c prime, two different scalars, c prime times x is the same as multiplying c times the vector c prime x. And we have distributive laws, c plus c prime times x is cx plus c prime x, and c times x plus x prime is cx plus cx prime. So all the natural properties that you would expect for vectors under vector addition and scalar multiplication hold in Rn or in Cn. And we can use properties of vectors to write solution spaces of equations in a very nice way. Let me just define one other simple operation of vectors. If x1, x2 up to xn are vectors in Rn, and c1, c2 up to cn are scalars in R, then I can take the vector x1 and multiply it by the scalar c1. I can take the vector x2 and multiply it by the scalar c2, and so forth. For each of the vectors, I can take the vector xn and multiply it by the scalar cn. And now I have these vectors, and I can add them up. And this is called a linear combination of the vectors x1 up to xn. So we have, once you have an operations of vector addition and scalar multiplication, you can look at linear combinations. So let's go back to the equation 4x plus 7y equal 5. We saw that a solution of this equation, xy, had to be of the form x (5 sevenths) minus 4 sevenths x. Let me write this as a sum of two vectors. I can think of this as, this is the vector 0, 5 sevenths, plus the vector x minus 4 sevenths x. Because when I add these vectors by coordinates, this is what I get. And this vector on the right, so I have 0, 5 sevenths. I can write this as x times the vector 1 minus 4 sevenths. Because if I take this vector and multiply it by the scalar x, this is what I get. So my solution space for this equation, we call it W, is the set of all vectors of the form 0, 5 sevenths plus x times the vector 1 minus 4 sevenths for any x in R. Let me look at one more example. This is just using linear combinations to rewrite solution spaces in a somewhat elegant manner. So we had looked at the equation 3x minus 2y minus 5z equals 17. And we saw that every solution was the form x, y, minus 17 over 5 plus 3 over 5x minus 2 over 5y, which I can think of like this perhaps. This is 0 plus x plus 0. That's equal to x. 0 plus 0 plus y minus 17 over 5 plus 3 over 5x minus 2 over 5y. I can write that as 0, 0 minus 17 over 5 plus x 0, 3 over 5x plus 0, y minus 2 over 5y. See, I'm collecting in a certain way the coordinates that involve just x, just y, or just numbers with no x or y. And finally, I can write this as 0, 0 minus 17 over 5 plus x times the vector 1, 0, 3/5 plus y times the vector 0, 1 minus 2/5. And so I can say that my solution space for this equation is the set of all vectors of this form for any choice of x and y. So this is a nice way to write the solution space. And we'll see very soon why this is, in fact, extremely useful and not just aesthetically pleasing. So this is section 1.2, and that is it for this small lecture.